Just started.
Okay, cool. All right, so current. Wow, that's an interesting way to start. What was that?
A toaster.
Oh,
I
thought you did that on purpose.
Okay, that was one of my multimeters, I think. They beep sometimes. Okay, so electrical current, if we're going to use the river analogy, is like water flow. Okay, now physicists would maybe get a little bit mad at us for comparing current in a wire to water in a river. Okay, because it's not a perfect analogy by any means, but it's a good way for us to understand this. Okay, so again, you guys knew I was going to talk about rafting, of course.
I can't really see.
All right, so that's a kayaker, and does anybody know what rivers are measured in for current?
You say it.
Flow rate.
I say it sometimes, yeah.
FC.
What is it? See,
Speak up, man.
you guys all look at Melanie.
It's like
CFS, okay, cubic feet per second. So if you picture a basketball, okay, that's a cubic foot. It's how many basketballs are going by a point in the river every 1 second. Okay, now it's obviously water instead of basketballs. So let's look at this. This is a little creek, okay? If we measure a point on that creek, and let's say we have...
Stop.
Let's say we have 12 cubic feet coming by that point every second, okay? That would look like this, 12 of these every 1 second. Now this creek is probably flowing at a lot more than that, okay? But that's just an easy visualization. Okay, now what about a slow point in the creek? Here's the deal, it's weird, okay? A slow point in the creek still has to be flowing at 12 CFS, okay? Because if it wasn't, then there would be different amounts of water flowing past different points at the same time. And then wouldn't water build up in places? So the flow is actually the same everywhere in the river, but at a slow point in the river where the water's not moving as fast, what must be true? It's wider and or
deeper.
Deeper. Okay? So it would be like this. So this is like the Colorado River through town. It's just wider, all right, or deeper. Okay, does that make sense? All right, you can either have that or you can have this. It's going faster, but the river is constricted. That's like a rapid. That's like right here. Okay? All right. The Mississippi River, 500,000 CFS. All right, huge, huge river, right? I love these graphs. These graphs are so cool for my friend. Okay, I look them up. You can look up the CFS for any river in Colorado. This is the Colorado River right out here at the state line. Okay, and the epic flood year of 2011. Does anybody remember that? Okay, check this out. 50,000 CFS. All right. Oh wait, I'm busy. Okay. That's the highest I've ever seen the river get up to. Okay. Here's another runoff here. Okay, so you guys notice I've started these graphs at April and gone through June because that's when runoff happens. So you can see that the river goes up and down a bunch of times and then it peaks. So that's 40,000 CFS. Right now outside it's only at like 1,800. Okay, so big differences. Okay, now electrical current. Alright, let's pick a spot in a wire and let's see how much charge goes by that spot per second. Okay, you guys see how it's kind of the same thing? Alright, except with electrons rather than water. Okay, rather than basketballs of water. Okay, so if rivers are cubic feet per second, what must the unit of electrical current probably be?
Charges per second.
Okay, electrons per second.
Coulombs.
I heard someone say charges per second, coulombs per second. Okay, and that's what it is. Electrons flow by any given point each second. So the unit's coulombs per second. On your notes there under unit. We haven't gone over the variable yet. We'll do that in a minute. Okay, now, do the electrons really flow like this, like water in a pipe? Actually, no. Okay? It's actually a little different than that, but charge is going by. Okay? Alright, now we shorten this to amps. That's the actual unit that we use. Rad amps. Okay? And to shorten that even further, we'll just put a capital A. Alright, just like we put a little m after meters, after distance, we'll put capital A for amps. Okay, now let's, just to put it in perspective a little bit, 12 amps. I have a 12 amp circular saw at my house. Okay? That's like a common power tool amperage. That means 12 coulombs of charge per second. Okay, so let's see how many electrons per second that would be. Okay, well 1 coulomb, isn't 1 coulomb that many charges? You guys remember that funky number there?
No.
Okay, no? We did that like yesterday, guys, come on! Okay, so we multiply that and that, that's electrons per second.
Holy crap.
I know. Scientific notation is our friend, right? That's how many electrons per second. Okay, electrical current is a very powerful thing. We can do some cool stuff with it. Alright, so let's take a look at some more blanks that we need to fill in on our notes. Alright, and okay, and variable. Current is I, capital I. Okay, units are coulombs per second, which are amps. Okay, so let's do an example that deals with this. 18-1 down here. Okay, steady current of 2.5 amps flows in a wire for 4 minutes. How much charge passed through any point? Okay, so here's what we know. We know that the current is 2.5. The time is 4 minutes. Okay? Oh, he's not here.
Okay.
Thank you. Okay, so let's do this. We're going to do some unit analysis here. We got 2.5 amps. But amps is just coulombs per second. We're really just doing some unit canceling. Okay, now what do I want to get to?
Minutes.
Well, I'm going to use minutes, but my answer needs to come out in just coulombs. So I need to cancel the seconds down here. So what I'm going to do is put seconds up here. I'm going to multiply by the time in seconds. So I've got 4 minutes. So 4 times 60. Alright, and that should get us the answer. Okay, so let's multiply that out. Alright, and we will get 600 coulombs. Any questions? Okay. Alright, how many electrons would this be? Okay, we just have to take our 600 coulombs. And how many electrons are in 1 coulomb? 6.24. 10 to the 18th. Now you don't have to have that number memorized. It's on your useful data table. Okay. get 3.74 times 10 to the 21st. E minus. E minus. I'm having trouble talking 7 power. Sorry.
What does the E minus mean?
That just means electrons. Okay? Alright, now people always want to know, okay, what about current in the human body? What's the deal with that? Okay, so here's the deal. 0.001 amps. Okay, if you have that running through your body, you will just barely be able to feel that. Okay, so that's 1,000th of an amp. 0.005. How many of you have been shocked before? Yeah? Whoa, like most of you?
Like what type of shock?
Electric fence.
Electric shock, yeah.
Like exposed wire kind of?
Yeah, like an exposed wire or something like that. Okay, if you get 0.005 amps, okay, this is kind of like the threshold of pain. Alright, so that does not feel good. Getting shocked is a really horrible feeling. Nobody likes to. Everyone I've ever talked to, it's a bad feeling.
It's my favorite.
Okay. Okay, 0.01 or 100th of an amp.
Death.
Spasms.
Oh. It's like a taser?
Yeah. So involuntary, by the way.
Can you have a
Alright, so involuntary spasms, your muscles are going to twitch a little bit. Okay? Alright, or if you grabbed a wire or something, your hand was kind of blown back off that wire. Okay, that's what this is. Okay, 0.015. Total loss of muscle control. Okay, don't our muscles run on electrical impulses?
Yeah.
In Fox's class, they probably cover that pretty hardcore, okay? Alright, now if we get a bunch of current in there, isn't that just going to kind of override what your brain is doing? Because your brain current is not near that much current, okay? So, it's going to cause some bad stuff to happen. Okay, 0.07 can be fatal. Okay, now I'm going to put a parenthesis here through heart. 0.07 amps through your heart. That can kill you. Okay? Yep. Question.
So like if you got shocked in the head with 0.07, could you...
Well, yeah, if it went through your brain, probably. I don't know. I'm not sure. Okay, through your heart is the main thing they talk about. That killing you, but yeah, could that do? It might kill you if it went, ear to ear or something like that. Trevor?
I thought it was 0.05.
Well, it probably depends on where you look up the numbers. One site might say 0.05 is like the threshold, and it might say 0.07 will definitely kill you. Yeah, so is there a range, and does it depend on who you are?
Yeah, probably.
What if your heart is very resistant to electrical shock?
Might be a robot.
Yeah, there's not one solid answer to that question. Okay, Melaine?
Where does a static shock go on that stuff?
Where would a static shock be?
Yeah, like
Okay, well here's the difference,
wearing
guys.
slippers and-
That's a great question. The Van de Graaff over there, you guys received some little static shocks, didn't you? If you didn't follow instructions.
I wouldn't know.
Or some of you wanted some static shocks. But the thing about a static shock is it is a one-time jump. Okay, now if I stood there and pointed my finger over, it would jump. Okay, and it'd keep doing that, but it's not a constant flow. That is the huge difference. Current is a flow continuous. Alright? So you see the difference? Now, lightning is a really big static shock, right? Okay, but lightning carries an insane amount of energy. Okay? This battery right here actually has more charge than a lightning bolt. In fact, this has like 5,000 coulombs in it. A lightning bolt has like 15. But the energy behind this charge, this is at 1.5 volts. Okay, lightning, 50 million is the number I have at the top, in the top of my head. Okay, but don't go in that. Sierra?
So then what is a defibrillator?
Okay, now a defibrillator operates at very, very high voltage, but low currents, okay? And I don't know exactly what current it would be, but I imagine it's somewhere in here, okay? Because it needs to be enough current to kind of jumpstart that heart back into motion, okay? And that's why you see the nerves make the body, or the patient, I shouldn't say the body, jump, right? Okay, so I imagine it's in this range, but they do operate at high voltage, low current, okay?
So these aren't static shocks. These are like, if you were
These
to
are
get
current.
like electrocuted, just like keep electrocuting you, but like
Yeah.
just the pain would be different.
Well,
Like,
sure,
for-
and you know, it does, time is a factor as well.
Like point.
So how much time this current is acting on you is gonna make a big difference, right?
But like 0.01 would be just like a constant little shock, but like 0.07.
Well,
would
if
be-
you had 0.07 through your heart for a couple seconds, that would be enough to stop it.
Yeah, but it doesn't like go and then jump off. It like would keep going.
Yeah.
Like static just. goes
Static
and
is
jumps.
just a,
Jump.
it's a jump. Okay, now let's look at this. Okay, Mitchell, can you see the meter on the screen and then maybe me as well?
Yeah.
Okay. All right, so we're gonna start connecting circuits a little bit today. All this stuff that I'm kind of playing with up here, you'll get a chance to do labs with as well.
You mind?
We love playing with wires and meters and Christmas lights and everything like that in this unit. Okay, these are called alligator clips. All right, they are wires that we can use to connect components into circuits. So let's do this. Let's take a Christmas light. And what do you suppose this measures?
Amps.
Amps, current, okay? Hence the big A there. All right, so I'm going to connect that there. And then we need a voltage source to get current from, right? So we'll take our battery set here. And we have all kinds of things we can use as voltage sources. Put that right there. And a circuit always has to be a complete loop. Okay, so when you're connecting this stuff, you can kind of connect it in a circle, like I'm doing right now, to know that you've completed the loop. So you guys see how this is a big circle?
Not really.
No.
Well, it's not a complete circle yet until I go like that. And then sometimes your light bulb doesn't light up. Okay? We can try a couple things. More power. Oh look, it's still not lighting up. Okay, what should we do?
Get into
New light bulb.
What gauge of wire are you using?
This is very, very small, cheap wire. Okay, now do you guys see that needle jump right there?
No.
No.
Let's dial this out so you guys can see the whole system. Okay, now jump to the negative, so I actually need to switch these two wires. Okay, and look at that, I maxed out the scale. Okay, when that happens, you want to use a different scale. Okay, that's an appropriate scale. So this is the 500 milliamp scale. You can see that down there. All right, and so I'm reading the top portion there. How many amps do I have?
100.
Okay, it's between the 100 and the 200, so let's say it's 150, but that's milliamps. So how many amps is that?
Like 1.5.
0.15. Okay, now let's look at this. Let's run 3-volt battery. Okay, did you guys see what happened to the light? Got a little brighter. Now I'm at 200 milliamps or 0.2 amps. Okay, now we just talked about the current running through the heart. Okay, if we had 0.2 amps, isn't that way over what we can take? Isn't that way over what can kill
It's
us?
like double.
Isn't it like
It's more than double. It's divide 0.2 by 0.07. Somebody.
Oh, you actually.
What do we get?
2.85.
So it's 2.85 times. Yeah, okay, now let's keep going. Look at this. 4.5 volts. Now we're at 250 milliamps, and then 6 volts. 6 volts will put us at 300 milliamps, and you notice the light gets brighter each time. Okay, so more voltage, more what? Current. Okay, they are directly related. That is part of something called Ohm's law, which you will know very, very well. Okay, so what's the deal here? I'm getting 300 milliamps, but I'm allowed to kind of play with these wires. Like, should I not touch these? Bzzz. Okay, why is that not dangerous? Alright, I can walk up to these batteries, alright, and I could unscrew these right here, and I can touch the metal in there. Ain't no thing. Okay, why doesn't that, I could walk out to my truck right now and grab the 12 volt battery terminals.
Because you're not a conductor.
You're not a good
Okay, alright, not a good conductor, that type of thing. Okay, the answer really is what we're going to study next, which is resistance. Okay, that will be the third piece of the puzzle here. Okay, any more questions on current? Connor?
So you always talk about like physics busting movies and stuff, but I can't think of the name of the movie, but it's the one where he has like a bunch of